satisfy simultaneously the new model and the observations. Yeah?
Assalamu alaikum.
However, if you take the new
Donc avec vous,
model,
Madame
the observation,
Bertossi,
and you make the extra assumption
je suis en
that
train de vous
nothing is
enregistrer
abnormal, I mean
un
that all the
webinaire
gates are perfectly okay, then you get
proposé
inconsistency as
par
well. Again, because you are assuming now that the gates are not
c'est
abnormal.
un COSI
So
webinaire,
basically,
c'est
you
la
are back
conférence COSI.
to the ideal circuit. So it has to be abnormal. But now this allows us to play a bit, and that is the interesting part, right? For example, this is inconsistent, but if I start changing some of these literals from negative into positive, for example, saying A is abnormal, yeah, maybe I can restore consistency, yeah, and that would be a strong indication that there might be a diagnosis hidden here, right? So something has to be abnormal, otherwise this theory is inconsistent. So D saying that the gate or gate is abnormal is a diagnosis, because making the gate O abnormal restore consistency. Basically, you see what I did, I changed this not abnormality of O, of the OR gate, into the abnormality of OR gate, and now we have consistency. We
Donc
have restored, and by definition,
webinaire
then the
parle sur
abnormality of
l'explication
O
des
is a
décisions
diagnosis.
prises par
Basically,
l'intelligence
what we are saying,
artificielle,
the
IA.
cause for the
Donc le thème
malfunctioning of the
c'est
circuit is the
Explanation
abnormality
in
of the
IE
malfunctioning of the OR gate.
and
Yeah?
explainable
So we can say
AI.
the abnormality of gate O is an explanation for the
Présenté
malfunction of
par
the
le
circuit.
professeur
But also, if I
Leopoldo.
have D prime now, saying that all the gates
Donc
are
je vous laisse.
abnormal, it is also diagnosis,
Voilà, c'est le
because if I
professeur
make all of them
Leopoldo
now abnormal, I'm going to restore consistency again, so this is going to be consistent. But of course, I mean, this is
Donc il présente des
making
slides et il est en train
possibly too many
d'expliquer.
things abnormal. Here I'm restoring consistency, changing only one of the literals. Here I'm changing two of the literals. So it is a diagnosis, this new one, but maybe we would prefer the previous one because it is much more informative. Because saying that everything is wrong, I mean, it's not very informative, right? Yeah? So D is better. And of course, there are all kinds of notions here and here that about how to formalize this. But I think the intuition is quite clear, and formalizing this is not difficult. Like you can always not talk about minimality of changes, etc., etc. So D is better than D prime. You are making fewer assumptions about the normality. It's much more narrow than this one that is very wide as a diagnosis. It is more focused on the OR gate in comparison to this one that is declaring everything as normal. But indeed, D is also much more informative. Yeah. So this is what is called consistency-based diagnosis. It was introduced by Ray Reiter in 1987. People do not hear much about Ray Reiter in these days, but he was one of the most prominent AI researchers in AI in those days. He influenced many people. In particular, I had the honor and the privilege to work with him at some point. He was a big person in AI. Yeah? Yeah, now I can, so this is basically a very simple example of consistency-based diagnosis, but I can't go a bit further. I mean, now I could maybe bring some notions that are being used in the present, I mean, in the context of explanation. For example, could I assign a scores to diagnosis? Can we assign, I mean, this is diagnosis, but I could say this is a stronger as a diagnosis. It's better. Can I do that in numerical terms? I mean, right, and say assign a number, a score. Yeah, that is what people do in these days. Yeah? But I'm going to come back to this because actually this notion of assigning a scores is related to something that people are doing much more recently in AI. I have used this notion of causality, actual causality in my own research in the last few years. So now we are going to take a look at this same example from the point of view of actual causality. Yeah? So this example again can be cast as a causality detection problem. So we have the same situation as before. I mean, this is the circuit working in an unexpected manner. We have the model as before, saying that when the the gates are normal, they behave as expected. We have this kind of meta observation. I have been talking about observation, I mean that is observing 1, 0, 1, and 0. But here we have something like a meta observation, a higher level observation, right? Saying that all this is inconsistent. Yeah? The combination of the real low-level observation together with the model, plus the assumption that everything is fine, we saw that that is inconsistent. I want to see if I can change it. And we already saw that we can change this. Now, now let me introduce some notions that come from actual causality. The notion of counterfactuals. If you read the recent literature on explainable AI, you are going to find almost everywhere the notion of a counterfactual. What is a counterfactual? It basically are hypothetical changes or interventions on, in this case, non-abnormalities into abnormalities to see if something changes. In a nutshell, basically, a counterfactual is an hypothetical change of a variable to see if that changes other things, right? And by detecting changes due to the interventions, you may end up finding causes for whatever you are observing. Yeah? That is the intuitive idea. Yeah? This can be, of course, formalized in very precise terms. So here I am performing an intervention. You see, I am changing the value of ABO here from negative to positive. This is an intervention. It's a hypothetical change. And now what I see is that this counterfactual change leads to the change in the meta observation. Now it is not inconsistent, it becomes consistent. Yeah? So it has this counterfactual change has an effect at this meta observation level. So we can say that the abnormality of the OR gate is a counterfactual cause for the observation. Yeah? This is the idea. So I'm trying to connect, this model-based diagnosis with this much newer notion of actual causality. On the other side, if I change here, I'm intervening the other variable. I am making the A gate not abnormal, keeping the other as abnormal. I am making this A gate, the AND gate, abnormal, and the other is left as not abnormal. As okay. Right? So the meta observation that don't change, actually this is still inconsistent. So basically the problem with the circuit is not focused or due to the malfunctioning of the A gate. Yeah? So this is not a counterfactual cause because it's not changing the meta observation. Yeah? So in this case, in order to maybe make this something close to a cause, I have to change other variables. In this case, there are not many options. I will have to change this one. So I need this additional contingent, what is called a contingent change, in order to make this something like a cause, right? So if I change, in addition to this, I change this one, I make this contingent change. Now I change this meta observation, the theory becomes consistent. So, however, this is an actual cause alone, without company, without additional contingent changes. I'm not going to say that this is a counterfactual cause, because the smaller portion is already one of those. So in this case, the abnormality of the A gate is neither counterfactual nor an actual cause. This is by definition, because the contingency ABO is already counterfactual cause. This notion of actual causality comes from the paper by Joe Halpern and Judah Pearl in 2001. It has been used in many contexts. Unfortunately, Joe Halpern died in February this year. He was a towering figure in AI and many other areas of computer science and beyond. Okay, but actually, Joe Halpern, in a later paper with Chokler, they took this setting of actual causality and they introduced a numerical notion, yeah, scores, that we are going to try to take advantage of. So the question that we had before, and we still have here, is is there anything like a numerical attribution score to quantify the strength of a cost? I would like to give a number, for example, to this abnormality of the OR gate. Yeah? And this is where the notion of causal responsibility enters into the game. As I said, it was proposed by Stockland and Halpern in 2004. It's a very interesting notion. Here, informally, I would say, I will retake this in a more general setting, but basically we can say the responsibility of the counterfactual cost abnormality of O is abnormal, the OR gate is abnormal, has a certain responsibility in the malfunctioning of the system. It's defined this way, it's 1 over 1 plus the minimum cardinality of a contingent set. That means the minimum number of additional changes that I need to make this abnormality of O a counterfactual cost for the malfunction of the system. In this case, I don't need anything. Actually, if I take a look at this, it was here, it is good enough to change the abnormality of the not abnormality of O into the abnormality of O to produce the change that we are observing here. So it doesn't need any company, no additional changes. So in this case, the number of contingent changes associated to the abnormality of the OR gate is 0. So it's actually the causal responsibility becomes 1. That is the maximum responsibility that the variable can take as a cost for some observation. The responsibility of A as a cost is 0 because, as we saw, it is not an actual cost because it needs changes, and those changes, additional changes, by themselves alone, they are already a cost. So that is qualifies the normality of A as a possible cost. It has 0 responsibility. So this is more or less the notion of responsibility. I have been using this notion very heavily in the context of data management, for example, to quantify what is the responsibility of a tuple or the contribution of a tuple to a query answer or to a violation of a constraint, etc. So you can apply these notions in database. So we will concentrate on attribution scores as explanations. I mean, explanations that are given in terms of numbers that reflect the strength of those values as a cost for, for an observation or a phenomenon that we have in front of us. So there are different ways of giving the explanation. I will concentrate on attribution scores. It's a choice. So there is a connection between causality-based, it's a connection with causality-based on causal networks and extractional models using AI. I mean, if you're familiar with AI or a bit of AI, I mean, a causality, you're going to see sometimes, I mean, these causal networks. Actually, I don't think I'm going to spend much more time on this. I can make the slides available to you. I will send them to the organizers, I mean, so you can take a look at this. But basically, I can cast my diagnosis problem as a problem of expressed in terms of causal networks with a structural model. But I think how value in an input contributes to the label that we are observing from the classifier. And these methods, I mean, it is interesting here. This is a very, very crucial point. These methods based on responsibility scores, in general, they do not need or they do not have to use the internals of the classifier. Only the input-output relation is used. I'm not saying that this is the only way to obtain scores.
Ça, c'est le professeur Leopoldo Bertossi
basically a method that has to do with classifiers or systems that, from which we are only going to use the input-output relation without having to go inside. But I'm going to say something about that going inside at the end of my presentation. Okay, so for the moment we are treating the classifier as a black box. We have no idea what is going on. All I know is I can use some inputs and get some outputs. Yeah? So only the input-output relation is needed. So again, let's just for simplicity, I'm going to assume that an entity, the entity could be the guy who was applying for the loan, right, at the bank, gets a binary label. I mean 0 in this case, one or 0. Yeah. So the question is, do changes of feature values, or in other words, intervention of feature values, change the label from 0 to 1? That is the question. That is something that I could observe just using the input-output relation, right? The idea, I mean, this could be the initial circuit malfunctioning or not, I have no idea, or any classifiers for binary entities, yeah? Or any binary classifier for binary entities. Yeah? I'm going to give you the idea by means of very simple examples that I made up, right? So I'm going to show how this works by showing a very simple classifier with binary inputs and binary outputs. So this is basically what I have. I have a classifier C, it's a black box. Yeah, I have 4 variables. They take values 1, 0, 0, 1. Yeah, in this case, and I observe a label that is 0. We want an explanation. Why are we getting this value 0? Or in other words, actually what we want is to see how strong is the value 1 for x1 to obtaining the value 0, etc. How strong is the value 1 for x4 for obtaining the value 0? Yeah? That is the idea. Obtain scores associated to the values of the input variables that somehow numerically explain the outcome from the system. So, so this is the situation I had before. Huh? The same picture I had here. So we can start playing with this, right? So what I'm going to do for him, so I'm changing the first value, x1, that was 1 to 0. And I observe that it changes from 0 to 1 now. The label has changed. Yeah. So here we have what we call a counterfactual cost for the label equals 0. x1 equal to 1, that is the original value. That is the cost, not the change value, but the original value. And the responsibility is 1. It's a maximum responsibility. I don't need to make any other changes, additional changes to change the label. So it has a maximum responsibility. Yeah? Okay, let's see other possibilities. Okay. Now I'm changing x2, but keeping x1 as it was. Yeah. Now I observe that nothing changes. So x2 alone, changing the value of x2, doesn't change the output. Yeah. So we concentrate on x2. It's not a counterfactual cost because, as I said, it doesn't change the label by changing it alone. However, let's now take a look at this. I'm going to keep x2 as 0, right? X2 as 0, yeah, the same input. But now I'm going to change these other 2. Yeah. Here now x3 becomes 1 and x4 becomes 0. And now I observe 0. Nothing changes. Yeah. However, now I'm going to make this additional change of x2 to 1 that I had made before without any interesting effect. Now, what I see here is that if I change x2 to 1, and in addition, I change x3 and x4 to the opposite values, I can see that these x3 and x4 act as a contingency set for x2. Yeah? I mean, if I change x2, and in addition, I change the values for these other 2 variables, then I change the label, which is what I wanted. So, assuming that these are the only additional changes that would help x2 to change the label, I could say that the responsibility, the minimum contingency set for x2 would have a size 2, because I need to make 2 additional changes. Yeah? So, So here I'm just explaining what I did. Changes on X3, X4 do not change the label. That is what I showed. The change on X2 accompanied by changes on X3, X4 does change the label. So we can say that X2 is an actual cause for the original label, and we can say that X3, X4 is a contingency set for X2. Yeah, they are additional changes. And if gamma is the minimum size contingency set for X2, then the responsibility of X2 would be 1 over 1 plus the cardinality of this contingency set, that was 2. So I get 1/3. Yeah? So that is the way things work, right? This is the notion of responsibility for binary classifiers, and it has been used in many situations for classification, for explanations in data management, etc. And I'm not going to talk about this today. So we say that this is a counterfactual version of the original entity. You see, the original entity was 1001. This is a counterfactual version of the original entity where I change 0 to 1, this other 0 to 1, and this 1 to 0. It's a counterfactual version of the original entity. And sometimes these counterfactuals are interesting by themselves. I mean, not only just to compute the responsibility score. This will tell us, then if I can make these changes, I obtain what I want. Maybe I will change this. But okay, let me try to show this in the light of the example we started with. So back to our banking example. I have a loan, again, request, they classify answer no. This is the feature vector representing the entity. We have here, if we change 18 to 25, well, maybe we get yes now instead of no. So this would be a counterfactual version. Well, is it useful or not? Well, maybe it's not very useful because, I mean, that means this guy will have to wait for 7 years before applying for the loan again, right? So it's a counterfactual that may not be very useful. Yeah. So the value of feature age is a counterfactual cost with explanatory responsibility, in this case 1, because only one change changes the label. But this could be an alternative. So in this entity, I'm changing the salary from 70K to 80K, and now the guy is moving from Harlem to Brooklyn, hypothetically, of course, and now I change the label. The guy gets the loan. So the value for income is an actual cost with responsibility 1/2. I am simplifying things a bit just to give you a gist because there are some issues. So the important thing is one needs additional changes. It is not about just changing the income. I need also to change the neighborhood where he lives. That is the idea. Yeah? Well, actually, well, maybe this could be a counterfactual that is more useful than this one, because maybe the guy could change job. I mean, I get a 10K increase and change from Harlem to Brooklyn. Maybe that would be a counterfactual that is useful in practice. Those counterfactuals that can be applied in practice and used in practice, they are called resources of or resources. I mean, they are counterfactuals that can be put to work, can be used in practice to make a real change, not just an hypothetical change. Yeah? They also call actionable resources, I mean, actionable counterfactuals. Yeah, they can lead to an action, right? A change in reality. Yeah? So these are important in the literature. I don't think I will. I have some slides on that, but I don't think I will be able to go into that. Well, but now the question is the following. Notice, I change 18 to 25. Yeah? But what happens if I change 18 to 24? Let's assume it is no. 18 to 26, let's assume it is no. Or I don't know, maybe if I change 18 to 25, is the only possible change that will change the label, but the ages, they will go from 1 year up to, I don't know, let's say 120, let's say. And for all of the others, there is no change. Well, actually, the responsibility of 25 doesn't look as strong as before, right? As in the situation where we have binary features. So when we don't have binary features, actually you have to be a bit more subtle about defining responsibility. And that is something that I did in work with Dan Suchu and other people. We took care of the situation where the features are not binary anymore. And in that case, you have to consider, for example, how many times, how many situations you are in position to change the label, and how many we are not. So basically, you have to take averages or expected values, assuming something like a probability distribution on the domain. Yeah. So for binary features, the definition I gave before of responsibility works perfectly fine. But in the case of the classifier, possibly many new values for a feature do not change the label, and a few of them do, like they change to 25. Right? So then the original value is not a great explanation, or that shouldn't have a very high responsibility. So the responsibility score has to be generalized, and we did that in a paper with other people, and I think it was interesting to do that. So basically, the idea in that paper is that we have to consider the contingent features and values for them, and then take average of labels, right? We have to take into account how many of the values change the label, how many of those do not. Yeah. So you have to bring something like expected values, and if you introduce expected value, you have to introduce, of course, some probability distributions on the population, yeah, from which you are taking the entities. Yeah. Uh, uh, Still, in that paper, we were considering binary classifier with label 1 or 0. Of course, all this could be generalized and produced in a mega paper, but I mean, we stick to the case where we have binary classifier, but now the features, they do not have to be binary anymore. Yeah? What is important to mention, because I have a slide on this, but I'm not going to show it because I think this is going too far. What is important to mention here is that responsibility is a local explanation score. It is a score for a feature value in a particular entity. It doesn't say anything about the global behavior of the classifier. It's for one input and a particular feature value in that input. Yeah? So we want to explain what is the effect, or how strong is the age of the guy who applied for the loan to obtain a negative answer. Yeah? So there are also global explanation scores, but I have to, yeah, see, yeah, this is generalized responsibility, but I'm not going to go into that. The only thing I want to see you is that at some point here, you have to take expectations, right? Basically average. And for this, you need something like a distribution on the population. Uh, so I think this is an interesting paper. I mean, but of course, what we show in that paper is that this restricted that this extended responsibility is intractable, right? Because it depends on the probability distribution. So you easily find situations, certain class of classifiers for which, I mean, computing responsibility becomes sharply hard. I already mentioned this notion of actionable explanation and resource. I mean, those are these counterfactuals that can be used in practice. Those are counterfactuals that make sense. Yeah. And this is there is a whole area in the context of explainable AI around resource of actionable counterfactual or explanation that lead to real changes in the world that can make a change possible. And specifying and reasoning with counterfactual is actually very useful, because you have competing counterfactuals. You want to compare them, which of them is more suitable for an application in practice. I have some slides on this. I don't think I'm going to have the time to cover that, but I have a paper on reasoning with counterfactuals. So reasoning with these scores and reasoning with counterfactuals is a very interesting subject by itself. Okay, let me talk about something different. The Shapley-value. This has been around for some time. What is the Shapley-value? The Shapley-value is, actually has found an incarnation in explainable AI as a SHAP score. Yeah? The SHAP score is based on the general Shapley value of coalition game theory. So this is something that has been around for some time. It was proposed in a paper by Lloyd Shapley in 1954 or something like that. So it has been around in game theory, and now the people in Explainable AI, machine learning, they have used this Shapley value as in a particular incarnation to give scores, local scores to feature values for the outcome of the classifier system. Yeah? So whenever you apply the Shapley value, that is general, as I said, it appears in coalition game theory. If you want to apply it, you have to find an appropriate gain function. Yeah? You need to find a gain function that is specific or useful for the situation that you are analyzing. So this gain function is basically a mapping, a function that sends set of players to real numbers. Basically, this gain function takes a set of players that, and for each sub-team or subset of the players, it gives a number, right? So in our case, we have to choose the game and the players. Well, in this case, the set of players F contains all the features relative to a given entity. In other words, I'm saying the gain function has as players the feature values for a fixed particular entity. Yeah? And I want to know how strong are the different coalitions, yeah? With respect to the outcome of the game, of the classification in this case, that I'm going to handle and model to this Shapley value. Yeah? So the gain function, again, if I take all the possible, for every possible subset of the features, yeah? Subset of the features, ES, I have a fixed entity. Think of the guy John, etc. For this S, with ES, I'm going to denote the projection of E on S. That means basically I am fixing the values for the features in the subset S, and I don't care about the values that are outside the set of features S. Yeah? So it's the projection, the usual projection that you do in databases, right? So what is the gain function now? It is the unexpected value that already tells us that we need somewhere a probability distribution, otherwise expected value doesn't exist. Yeah? So it is an expected label over what? Over all the possible entities, yeah, that belong to the entity population, yeah, and coincide for the set S with the values that the original entity has. Yeah? So basically, I am taking all the features that have the same values as E on the set S. I am letting all the other feature values vary in their domains, and I'm going to get for each of those variations, I mean simultaneous variation, a label. I'm going to get 1, 0, 0, 0, 1, 1, 1. Then I take the expected value of those classification outcomes. Yeah? But for each set S, I am fixing the values for E according to S. I am giving those values to all the possible entities, letting the other feature values vary in their domains. Yeah? So, and after that, I have to use the gain function. And the gain function is used using the general formula that was provided by Shapley. This is the only part where we are creative here in finding the gain function. The rest comes from Shapley. This is the formula for the Shapley value of what? What we want to do is we want to compute this score for a particular feature, F star. Yeah, I want to know what is the score, the relevance of the age, right? Actually, of the age of John, that was 20, I think, I don't remember. Yeah? And we want to compute its Shapley value with respect to the set of all the features and with respect to the particular gain function that I chose. Here, the Shapley value is defined as following. Basically, what we are doing here is basically consider how having this particular F star changes things. So I am comparing this gain function having F star fixed with the same value for the gain function without having F star fixed. Okay? So basically, it's a very small local change. Here I am using the gain function, fixing all the values for S, for the subset S, together with the value for F star, I mean the 20 that had this guy John, right? And here I only fixing the values for the set of players S without considering fixing the value for F star. That local mini difference may have an effect. I mean, you can compute the difference in the expected value. So basically, this is the expected change of label. I mean, when you locally change the feature, consider the feature value F star as a possible change. And then what you do, well, we have all kinds of subsets. So you have to basically add all these terms, right, according to all the possible subsets that are included in F minus the feature that you are analyzing, for which you want to compute the score. So you consider all the possible subsets of the set of features without the one in which we are interested. And then not only the sum, but you also consider all the possible permutations of the set of players S and all the permutations of the rest of the players divided by the permutation, the number of permutation of all the possible players. I don't want to go into that. This comes from the Shapley-value. That has nothing to, I mean, nothing specific to our scenario. The only thing that is specific to our scenario is the definition of the gain function. This comes from the Shapley-value. Why this formula, you will say? Because, well, Shapley-value shows, mathematically shows, that this is the only score that satisfies certain natural properties. So basically, he defined the Shapley-value axiomatically. He gave, I want a score that has this, and this property, and he proved mathematically that this is the only way to achieve that. So, and then we just use it, okay? Okay, the SHAP score has become quite popular. It was introduced in 2017, and there is a lot, I mean, a huge literature on the subject. Of course, it assumes a probability distribution on the entity population. Yeah? The other thing that is also important to notice is of here, you have to make a huge number of passes through the classifier, right? Because you have to are considering each of the possible change entities, right? You are changing values in the entity. You are making them pass through the classifier. So this is already you see. Look at this. You see that this is bound to be hard, right? So this is SHAP has become a most popular explanation score in machine learning. The Shapley-value, in particular, SHAP is probably intractable. So the how much time I have?
Sorry, would it be fine if you conclude in 5 minutes, just to let some times for question?
Oh, okay, I'm going to go fast. I mean, the question here is, Shapley is probably intractable. Can we do better at computing SHAP with an open classifier? If I know the components, I mean, that is the question that we pose ourselves, I mean, with some colleagues. If we have access to the structure, to the components of the classifier, can we do better in terms of computing SHAP in polynomial time? And I will go very fast through this. Basically, okay, sorry. Actually, I'm very close to finishing, so I think I can afford to show a bit of this. Okay, this is SHAP. This is the general formula. This is bound to be difficult. I am here. I'm only using the classifier as an input-output relation. I don't see anything about the classifier. So the question is, can we do better if we have more structure? For example, if instead of having a black box, I have a decision tree. This is very clear. I mean, maybe I can take advantage of this structure and compute SHAP in a more efficient manner. Not only the input-output relation. Well, what we show in a paper that appeared in AAAI a couple of years ago is that SHAP is tractable for a class of deterministic and decomposable Boolean circuits, for the class of deterministic and decomposable Boolean circuits. Yeah? It is denoted in this way in the literature. Under the uniform and product distribution. Remember that for computing SHAP, you need the product distribution. We analyze the case of the uniform and product distribution. SHAP, as I stated in general formulation in the previous slide, is still sharply hard under this distribution. So this choice of distribution is not what is making things easier. I mean, it's easy to analyze what happens under this distribution. But these are not the cause of the hardness. Okay, what is a deterministic and decomposable Boolean circuit? It's something like this. It's a circuit, a binary circuit. So the inputs are binary. X1, X2, X3, X4 are the inputs, binary. Here you have and OR gates. You can have a negation as well. The important thing is that, what is it? Deterministic means that whenever you reach an OR gate, the values of the arrows that go into the OR gate are different. Right? So that has to do with determinism. Whenever two arrows go into an OR gate, the two values are different. Yeah? You can easily see that this is going to be the case. What it means, decomposable. Decomposable means whenever you have an AND gate, the variables under one arrow, under different arrows, are all different. Here, this arrow has X4, this other arrow has X3, this other arrow has X2. So they are different. They do not share variables. The same here. This AND has X1, and this other branch, all this branch has X2, X3, and X4. They are not shared. So this means decomposability and determinism. That means that an OR gate is always reached with two different truth values. You can say, who cares about this circuit? I mean, why these guys are crazy? I mean, they're coming up with a situation that is completely irrelevant. Actually, that is quite relevant. First of all, if you get tractability for this class of circuits, you get tractability for free for a vast collection of classifiers via what is known in AI and other areas of computing as knowledge compilation for decision trees, even non-binary ones, using by one-hot encoding, order binary decision diagrams, tangential decision diagrams, etc. So it's a large class of other classifiers. I mentioned a few of them, for which we get tractability for SHAP computation, basically from the result for this kind of circuits. In particular, we get this for decision trees. And actually, the problem that was open at that point was whether it was possible to compute SHAP equal normal time for decision tree, and there was no answer at that time. So that was the motivation for our research. Well, we proved much more than that. But, okay, now the question is, I'm about to finish. What at some point with a student of mine, we thought about applying these mechanisms based on these circuits, I mean, for which SHAP computation is tractable, to situations that are different or cannot be compiled, at least easily, into these circuits. For example, what if I have a neural network? A neural network, I mean, cannot be expressed as a deterministic and decomposable Boolean circuit in a very simple manner. I mean, actually, it would be require a lot of work, and then also, I mean, the translation or the compilation could be very high. So we waste a lot of time during the transformation. So this is okay. So, but still, there was an interesting question. So what we decided was to let's take neural networks that do not fall in this category of classifiers, but let's take only binary neural networks, and let's try to apply this methodology to see if we get better results with the computation of the SHAP score. I am about to finish. Okay, so SHAP on binary neural network. So then we consider, usually neural networks are considered as black boxes, yeah? But we experimented with SHAP computation on a binary neural network by a compilation into one of our circuits, yeah? So here is binary in the sense that the input and outputs are binary. However, the threshold functions that you have at the gate, they could have real numbers. I mean, that is not the issue. The important thing is that you have input and outputs that are 0 and 1. Well, here I have 1 and minus 1, but that is just a practical technical issue. That is a minor technical issue. So we experimented with SHAP computation with this kind of something like this. So how does it work? First, we take the network and we transform it into conjunctive normal form. That is the formula, logical formula, propositional formula that is in conjunctive normal form. Yeah? So basically, it's a conjunction of disjunctions of literals. Yeah? There are different ways of doing this, different mechanisms in the literature. We just borrow some of them. We try to do that in a very clever manner, I mean, and also optimized manner. And then, once you have the conjunctive normal form, that's a logical formula, you create from it what is called a sentential decision diagram. Yeah? A sentential decision diagram is a decision diagram that you have the input and output, the binary input and output, and then you make a decision, yes or no, or 1 or 0. Yeah? This transformation is not polynomial. So this is the place where things do not work properly as expected, in the sense that you don't have a polynomial time transformation. However, it is fixed parameter tractable. That means it is polynomial except for the size of the clauses in the conjunctive normal form, basically. Yeah? And then, after you have a sentential decision diagram, you transform it in a very straightforward manner into one of our circuits. So this part is easy, in quotes, this part is direct, and this is the part that is difficult, but not that difficult in the sense that it is fixed parameter tractable. Yeah? Yeah. So you will say, well, that you have a cost to pay here, but well, actually, it is still worth doing this because this is a one-time computation. You take the binary network and you produce our circuit. Actually, this is the real circuit associated to this network. You compute this only once, and once you have this, you can use it for computing explanation for all kinds of features and feature values. I mean, it's not that you are going to compute every time you want to find an explanation or a score or a SHAP score, you are going to compute this. You compute this once, and then you keep using it. So it fully replaces the neural network. So that is a nice thing about this. So it is still worth doing this because it's a one-time computation. And the target circuit can be used multiple times. So we experimented with a binary neural network with 14 gates, a bit larger than this. Well, the circuit was relatively large, okay? And then we compared the SHAP computation for the black box network. I mean, using this classifier, this neural network, as a black box without going inside, just using the input-output relation. Those are the values that are going to depict in blue. Then we computed the SHAP values using this thing over here. It's the open box circuit, yeah? I'm going to show in orange. And also but this is not particularly interesting. I mean, we also decided to use this as a black box. I am about to finish. Yeah? We use this as a black box as well, just to compare how this black box compared to this black box. Actually, we ended up paying a price here. But this is not the interesting computation, was just a curiosity. The important comparison is using this as a black box versus using this as an open box. And actually, we compute all the SHAP scores for all the entities with increasing numbers of entities, and we got this kind of behavior. This graph represents, as I said before, forget about the red. In blue, the computation of the SHAP scores as a black box. in orange the computation of the SHAP scores as an open box, as a circuit, and then you see, and this is in logarithmic scale, so you see a dramatic improvement in performance when you use this classifier instead of the binary neural network. I think this is quite interesting to observe. There is still room for doing research in these directions. There are still open problems, but I think this is already a very promising experiment and shows that this has potential. So the other thing I wanted to finish, just emphasizing why it is important to be able to reason with counterfactuals. I'm not going to go into this, but I would like to be able to reason with counterfactuals because, as I said before, the counterfactuals are not only used for analyzing what are possible actual causes for outcomes of classifiers or AI systems, they're also using in practice to make changes so that I can achieve a different result. For example, the approval of the loan. I'm going to leave with you these slides, and if you want, you can take a look at this, and you can always come back to me. I don't know if I don't know. I think that the address can be shared by the organizers. I don't think I have it here in the first page. But and I also very easy to Google and find. So please stay in touch. Here is my webpage, and you're going to find the information. Okay, that's it. Thanks a lot for the attention and opportunity to present a bit of my research and a bit more. Thanks a lot. I don't know if there are any questions.
Many thanks, Leo, for this really interesting talk. So let's move to the questions. Are there any questions? I see that there is a question on the chat. What about the neurosymbolic AI for explainable AI? I don't know if it's maybe it is from Nassim Latab. I don't know if you want to develop more, Nassim. If you are online.
Wait a second. I'm trying to go to the platform. Okay, what about neurosymbolic AI? I think that neurosymbolic AI by itself is not going to change the problem of explanations. Neurosymbolic AI has to do with a combination of symbolic method with, say, algorithmic method, because neuro is maybe too narrow. I think algorithmic method combined with logical method. I think, so neurosymbolic AI is not going to give you a solution per se, because that is not the role of neurosymbolic AI. However, I think having this combination of algorithmic and logical methods opens the ground for applying all kind of logic-based methods for providing explanations to be used, I mean, to provide explanations for these more complex systems that people are proposing. So I think this is a very promising direction, but you have to, of course, I mean, develop new methods of explanation in the sense that you have now a combination of systems, so you will have to end up explaining possibly parts that are logical and parts that are algorithmic or neural. So that, I think, opens new grounds, new research directions. But again, I mean, in a nutshell, I think neurosymbolic AI is not necessarily designed to provide explanations, but it may open new possibilities due, for example, to the fact that you already have a logical component there that you can take advantage of for providing explanation. But you will have to develop, in some sense, new methods for providing explanation in this broader setting.
Okay.
That is my take on it.
Okay, thank you. There is a question from Lilia. Please go ahead. Yeah, there is first Lilia and then Louari. Lilia, do you hear me? Please, can you ask your question? Yes? No. Okay. So, Louari, can you please ask your question? Because.
Okay. Thank you, Leopoldo. Thank you very much for the
Well, you're welcome. Yeah.
presentation. And I like the Shapley-value because with my colleague from University of Bijaya in Algeria, we work on this. And we are interested how to apply Shapley-value for learning. Exactly. Yeah. So my question, I have two questions. The first one is what you mean by player? What is the representation of player in the classification process or learning?
What is
A player?
Players.
what
are the players?
I mean, you have to define the players, right? For example, the Shapley value, as proposed by Lois Shapley, is an abstract mathematical model where you have these gain functions that basically they send subteams of players to real numbers. Yeah? And they have the Shapley formula that is general. As I said, it's not our invention, it's general. And all you have to do in order to apply the Shapley value in a particular setting is to choose the set of players, decide what are your players, and what is your gain function. That is what people have done in explainable AI around the SHAP value. Yeah? So in the case of explainable AI, machine learning systems, usually the SHAP values, the players are the feature values because they are competing in some sense with each other or collaborating with each other in order to produce an outcome, right?
Yes, yeah, exactly.
And in the case of, for example, databases, I mean, I want to know what is the contribution of a tuple database to a query answer. Let's assume it is a numerical query answer, a Boolean query. Then, in that case, the natural players are the tuples, database tuples. So all the tuples participate together because one single tuple alone is not going to give you an answer. Right? So you have tuples competing and collaborating with each other, and then you have to consider all those subteams, and then you try to find the
Okay. Okay.
So you have to identify the players. I mean, it's your job to say, I'm going to apply Shapley value with these players and with this gain function.
Yeah.
For example, let me one more. In the case of query answering in databases, let's say closed queries, Boolean queries. It could be a conjunctive query, yeah,
Yes,
0 or 1. In this case, it's very natural to define the Shapley value, the gain function as the query answer, the value 1 or 0. Yeah? And then you start comparing different teams to see if they give you 1 or they give you 0, and then you produce expected values.
Yes. Yes. My second question, you have talked about the complexity of computing the Shapley value, which is difficult for small example, and for learning. If we take player as tuple in database, it may be complicated because for learning we use huge data.
Well, actually, yeah, in databases it's also hard. Actually, yeah, I have a paper with Benny Kimmelfeld and other people, Stan Lipschitz, where we analyze the SHAP score, the Shapley value, sorry, not the SHAP score, the Shapley value for query answering. And actually, we came up with a dichotomy. For certain class of conjunctive queries, it is possible to compute the Shapley value in polynomial time. And for the complementary class, the dichotomy, you know that the computation is going to be sharply hard. Sharply hard means difficult, I mean, in this case. It has to do, why is sharply hard? I mean, because we are dealing in essence with counting problems. So that is the natural notion of complexity they use in that case, in this case. Yeah, so also, again, bottom line, even as an application of Shapley to query answering in databases, you can get hard cases.
Okay.
Yeah, we have another
Thank you
question
very much.
from. Thank you, Ruai. We have a question from Toria.
Hello, everyone. Thank you, Professor Leopoldo, for this very informative presentation.
Thank you.
So you have presented earlier some counterfactual methods to calculate the responsibility of features. But in order to do so, we need to try with many values for each feature. And this would be quite costly, even with like binary features, if there were many of them. So were there like some methods proposed to deal with this?
Well, actually, yeah. Let me go to the last slide. I mean, reasoning with counterfactual again is going to be hard. No?
Yes.
So the question is what kind of tools you can use to make this more amenable. So, and actually, yeah, I have a paper actually on that. I can give you the reference if you send me a mail. I have been using answer set programming. Answer set programming is basically take it as an extension of data log. I mean, and the important thing is that you specify counterfactuals. But also you can put in the program that specify the programs. You can put constraints, yeah, because some of the counterfactuals are not useful or do not make sense, but you don't want to consider them. For example, I don't know, you have someone who is applying for a job, right? The guy is, I don't know, it's an extreme case. It's 5 years old, yeah, and it appears in some other feature as married, right? Well, it is not. It will be in the original feature will be single, but you don't want to produce a counterfactual where he still is 5 years old and he becomes married, right?
Yeah. Yes. True.
Because there will be many combinations that do not make any sense. That do not, and you can. How do you avoid doing that? I mean, doing that by hand is very difficult, but you can, in a setting like answer programming, where you specify the possible counterfactuals, you can impose constraints on the kind of counterfactual that you want to consider. And that is very powerful because you can have general policies about what kind of counterfactual can be considered, right? And that is what I do in this paper, I think. And also, let me finish with it. Answer programming allows you to reason about counterfactual. For example, it will allow you to decide, are there two counterfactuals that are similar in a way that you specify in the program, but they give different labels, things like that? Or is there any counterfactual that leaves these values fixed, but changes these other values? I mean, you can reason. I mean, you can. There are many things that you can do with answer programming. I mean, that is